one has of about 1.4 to 1.5, which is higher than that of commercial PPC, about 1.2. This means that its OR activity is better than PPC. In addition, its limiting current density is also larger, showing that it can still maintain good oxygen reduction ability at a higher reaction rates. This feature shows the OER LSB polarization curve. For OER, the main parameter is the potential required to reach 10 million per which is E10. The lower potential means that the catalytic can drive oxygen.
你是在念上面的东西？
我这边有那个小笔记这样。
你应该这样子念。继续。
Oxygen evolution reaction more easily. In the figure, the E10 of LDH efficiency is about 1.59, which is degradation under high current operation, proving its good rate stability and discharge stability. The next feature shows specific capacity. It comes from a long-term constant current discharge test at 50 million per square centimeter. Specific capacity means how much charge can be delivered per gram of zinc. With the unit of million hour per gram, a higher value means better utilization. In the feature, LDH efficiency shows a stable discharge voltage of about 1.15 to 1.16, and the voltage drop rapidly after reach 818. This value is higher than PTC 803 and PTC plus RuO2 at 792, showing better outflow discharge stability. Finally, and this feature shows energy density. Energy density can be simply understood as the specific capacity times the average discharge voltage. Therefore, a good battery should have both high specific capacity and stable discharge voltage. The energy density of LDH efficiency is 956 watt-hour per kilogram, which is higher than PTC 946 and PTC plus RuO2 899. This shows that the catalyst not only perform well in OR and OER 3 electron tests, but also provide better energy output when assembled into a liquid zinc battery.
And next, I'm going to talk about the TAFL. The TAFL curve is common to use to evaluate the rate of the electrocatalytic reactions, and it is simply defined as an overpotential required to increase the current by 10 times. And the smaller TAFL slope means the current density increases faster, which indicates better catalytic activity. And in this two picture, we compare with the commercial catalyst. So at the OR part, the LDH, it has a slope of 86, and compared to the commercial catalyst is 97. And as the following say, the lower slope it is, the better the performance it is. So our LDH catalyst has the better performance than the commercial catalyst. And about OER performance, the LDH slope is about 107, and the commercial catalyst is about 126. And the LDH catalyst also has a lower slope than the commercial catalyst. So on the LDH catalyst not only perform better at the OR part, but also the OER part. And the
你们
next
注意这题啊
is the CV test, and we test the OR activity in a 0.1 mKOH solution saturated with nitrogen and oxygen. And in this figure, we can see that the oxygen saturated environment, our catalyst showed a strong reduction peak. However, after the nitrogen CV curve was flat without any obvious peaks, and this provides our catalyst has better electrocatalytic activity in oxygen compared to a nitrogen environment.
你这样说是错的，待会儿我跟你
And next is CA. This experiment tests the long-term stability of the catalyst during electrical chemical reaction, and we place in an oxygen saturated 0.1 mKOH solution at 0.6 volts and 1006 important as the last one CV test is the results. So this figure show after 50,000 seconds, our catalyst, the LDH catalyst, maintains a high current rate of 90%. In contrast, the commercial catalyst dropped to the 59.9%, and this demonstrates the excellent stability of the LDH catalyst. And next, because of the following task, and we are going to do the accelerated durability tests. And first, we do the CV test after 10,000 cycles, and we can see it doesn't have so difference from the original one. So it's the first picture that can show the LDH catalyst has a great stability. And the next one, we put this sample into the LSB test, and it's shown at this figure. We can see the halfway potential of the LDH only shift by only maybe 0.01 volts, just very small, just shift left very small. So we can see the commercial catalyst, they shift more than the LDH catalyst. So we can say that the LDH has better stability than the commercial catalyst. And the methanol tolerance is also very important because it can show the LDH catalyst solve the major problem of commercial catalyst. And in this picture, we can see the commercial catalyst that is sharp rapidly at 400 seconds after adding methanol. However, the LDH catalyst maintained 93.5% of its current after 1,020 seconds, and it showed only a slight decline and excellent performance of the LDH catalyst. And the next in this experiment, one cycle consists of 10 minutes of charge and 10 minutes of discharge. And it showed at the first cycle, the liquid thin air battery with LDH catalyst has discharge voltage of 1.35 volts and a charge voltage of 2.09 volts. And the load gas is 0.74 volts, and which it is matched to the potential difference from the previous ORR and ORLSB results shown at the right-hand side figure. So they're matched. And this is the long-term test results. And shown at this picture is compared to commercial catalysts. Our liquid thin air battery has better stability and lifespan. The test ran for 69 cycles, and we can say 120 hours. And in the final cycle, our voltage gap was 1.03, which is better than the 1.14 volts gap of the commercial mixture that only lasted 68 cycles, and also we can say 283 hours. And finally, the current density, we can see at this point, is 144. And we can see the LDH has the highest power density than the
So, first of all, why, so this figure, what does that yellow line?
你说这个时薪的线吗？ 我就是因为我这个是看人家的论文，然后我觉得可能它的就正常来说，它的这个应该要这个红线在这个部分应该要是最低的，然后这个部分它应该要再稍微高一点。我觉得是因为它的结果没有很好，所以它就有特别拿出来给我写，所以我就也没有特别说。
画的黄是为什么？
这个是就是我在最高点往下看，是看我的个人电视里是多少分值，我是从这个点往下看，然后来比较说谁最快。我是找
你要找450。
对啊，我就是看它的最高值那个 peak 这样子，那个地方。
最高是。
对，就是一般都会有一个小小的地方，所以我就找它那个。
你去看那个它是最高值。
对对对。
那最高值然后往下看就是这样。
对对对。
有 peak current density 知道吗？你刚刚说那一题啊，就是
这个吗？
你的 CA 是吧？CA 那张图，月平代表什么？
就是代表说它的就是你的触媒，它在经过长时间的反应，长时间的测试之后，它还是依旧维持它的效能等等，就是代表说我们就是它 LVH 触媒它是维持在90%的，但是就是贵金属的话，它就是会掉到大概60%这样子。就是它是在0.1 m 的 pH 的那个容易，然后0.6 volt， 然后1600。
为什么是不安全不安全？
文章里面好像没有特别说，但有可能就是说不定5万之后它的数据就没有这么好看，所以它就起了一个5万。
这是一个公认的一个实验，就是大家都是。13个小时。那个前面的那张图，你这张图说，就是说明在欧洲里面是好的那图是吧？你是应该不是这个意思。
可是它不是看氧化风吗？就代表它比较好的营养的话。
你去想一个问题。
好。
不是好跟不好的问题，是本来就是应该这样。是吧？有道理。不明白。
那它本来就应该有。
对啊。
所以是另外一个。
你如果水里面没有氧的话，会有化学风。是吧？没有氧。这个下一个。Okay, we can start with which one?
range with no significant oscillation current to see the electrolyte stability. And the last is preliminary screening of material properties using compared activity levels during electrolyte use. And this is how to test electrolyte UVC. We usually use the 3 electrode system is typically used. Yeah. And this is the CV diagram. When the potential is low, the current is small and relatively flat. And at this point, the potential is not yet positive enough, and the active material has not yet begun to undergo chemical reaction. The current is purely a background signal caused by changes in charge arrangement on the electrode surface. And it will climbing to the peak. And this is the highest one in the anodic peak. Anodic peak is we call it the EVA, the corresponding peak current at the peak current. And the lowest point is the cathode peak potential, and the corresponding current high is the cathode peak. And the next one is LSB. Why we going to test LSB? The first purpose is precising the determination of activity of electrocatalytic reactions, such as HER or OPR. This is the core domain of LSB. And the second one is measuring the onset potential. LSB can accurately capture the inflection point potential at which the current rises from a small background value. The closer the onset potential is to the theoretical value, the higher catalytic activity and the lower the resistance of the system in the electrolyte. And the third one is kinetic parameter calculation. By performing a transformation on the potential current data obtained from LSB, the K4 plot can be plotted. And we also use 3 electrode systems to test LSB. How can LSB be used to test and evaluate electrolytes? The first is test the electrolyte for hydrogen evolution, HER, or oxygen evolution, OER. And also it can evaluate the inhibitory effect of electrolyte activities on side reactions. By comparing LSB curves, if the potential for achieving the same current shifts to the negative direction after the addition of the additive, it proves that the overall potential has increased and the hydrogen evolution side reaction has been successfully suppressed. And this is the LSB diagram. We can see that in the middle there are 1.5 voltage and -1 voltage, and this area we can calculate the ESW, and the more ESW, the more stable during charging and discharge. And the next one is table. The main purpose of testing table, one is evaluate reaction kinetics, calculate the exchange current density. And the next one is analyze the reaction mechanics and resistance. And this is
researchers. This slide explains the main purpose of ADT. The goal of ADT is to stimulate long-term status weight aging with a much shorter experimental time. By repeating applying electrochemical steps, researchers can quickly evaluate the status, stability, and reliability. During ADT, several vegetation minimum can be observed, including acidity and reduction stress, metal dissolution, corrosion, surface construction, and mechanism.
Okay. Okay.下一个。这里第一题我们两个，因为是我们实验室要用的，是吧？是个很好的。
什么东西？
ADT 是一个很好的测试，我们要用。
嗯
对。好。
嗯。
你要开始这个东西。这跟你们研究相关吗？
有一个应该有点深入了，但是不是真的完全做的那种。我们做的唯一流到电的只有那个电流层，就是要测它那个做出来是不是我们要的长度。
你说黄老师的研究室。
对。
开始，想开始就开始。三个都要讲。
对。
说出来。
我在我。
The size of the semicircle is a key point. A large semicircle means a higher resistance and better resistance protection. First, for C1, C, SS, A and B, the semicircle become larger from day 1 to day 21. This means the field form a stable protective film over time, which improves its corrosion resistance. Second, for C1, and CUA, C and D, the semicircle form uses at the first 7 days, and the event becomes larger than that of C1, and SS. This shows the CUA has better good protection and durability. However, after 7 days, the semicircle becomes much smaller, indicating that the protective film starts to break down. Third, for the C1, and CUB, E and S, the semicircle stay very small throughout the whole test. In addition, a low frequencies, the curve change into straight line or a regular tail. This suggests that the cushion layer of the CUB is weaker and poorer, allowing ions to move through it easily and increase cushion. Overall, CUA shows a good protection only in the early stage, while CUB has poor cushion resistance throughout the test. The control C1, and SS show the most stable and durable protection over 21 days. And now, the early stage or control sample RS is solution resistance. The first parallel rule, 2F in the RF, represents the capacitance and the pore resistance of the surface biofilm or passive film. The inner loop, QBL and RCT, represent the double layer capacitance and the charge transfer resistance and the metal solution interface. D adds the Weber impedance W in series with the charge transfer resistance RCT. We use the specific one for the field bearing SS because the accumulation of those two products creates a diffusion barrier, which match the straight line we saw in the low frequency region of previous feature. The HS is time from 1 to 21 days, and the Y axis is RP value. A big RP means lower pollution rate. RP lower means a faster pollution. Look at the blue line. C1, and CUB, you can see the blue line is always low. It means C1, and CUB has highest pollution rate. Local did not protect it. Next, we look the red line for C1. In the end, is RP goes out to become higher than the field.
Next, we are going to talk about the sample polarization curves. First, let's look at the baseline performance in a zero environment, as shown in point 1.
presents demonstrates that copper contributes to a more stable passive layer promotion than the standard 316-liter stainless steel. Let's observe the curves in the SRB environment shown in figure B and figure C. Unlike the stereo condition, we see a distinct rightward shift of curves for all CU bearing steel. This indicates a significant increase in the corrosion current density, meaning the overall corrosion rate is accelerating due to bacterial activity. More critical, by tracking the pitching potential, we can see it shifts to more negative values in the presence of SRP. This tells us that the passive film has become unstable. It can no longer protect the steel at higher potential, and the material becomes prone to localized heating much earlier than expected. And then we're talking about mechanism integration. To understand why our electrochemical data shows such a decline, let's look at this mechanism. In the baseline stereo condition, the copper bearing steel acts as a stable barrier protecting the steel matrix from uniform corrosion. And however, when SRP bacteria present, the situation changes. Their metabolic acid reduce sulfates into sulfides. These sulfides react instantly with the released ions C. The copper ions, forming conductive copper sulfide deposits on the surface. This is the third. This is the turning point. This conductive the copper sulfide creates a galvanic couple with the steel matrix, accelerating the breakdown of the passive film. This explains why I observed the current density increase the heating potential drop in our polarization curves. The passive protection has been fundamentally compromised. Conclusion. Above all, our study reveals an electrochemical inversion. Copper provides a protective shield in stereo condition. SRB metal colic activity completely reverses this behavior, actually accelerating corrosion. Our connective analysis supported by the negative shift in speeds and the drop in the converses
是不是有另外一组还没开讲到？
对，就是还有
最后一组是吧？
对，剩这一组跟
你们也是周老师的学生。哦，是。开始吧。
The Alpha is research considered ionic chemical functional separators of zinc ion batteries. Zinc ion batteries have attached attention because of their low cost, high safety, and accurate electrolyte system. However, they still face some essential problems, especially zinc dendrite formation and hydrogen evaluation. In this study, we use GNA plus DNA to modify a glass fiber separator. The goal is to regular zinc ion transport and the interfacial water environment, and finally improve the stability of zinc ion battery. This slide shows the two charge of aqueous zinc ion batteries. The first one is zinc dendrite formation. During charging and discharging, zinc ion deposits and strings on the zinc So zinc ion graphs become more uniform. Zinc deposition becomes smoother. And the dendrite groups can be supported. So the main idea is the